Unit 4, 5, and 6, inshallah. Starting off with electricity and magnetism. Describe the forces between magnetic poles. Definitely, we do know the forces between the magnetic poles. We know that the north and north repel, south and south repel, north and south attract. Uh, like poles repel and opposite poles attract. Okay, and that these forces are there. Okay, the magnetic forces are there. Why? Due to the interactions between the magnetic fields. Okay, this is quite simple. Describe what is induced magnetism. Induced magnetism is the magnetism created inside the magnet. Okay, induced is created or generated. State the differences between the properties of the temporary magnets. We know that a temporary magnet is usually made of iron and that a permanent magnet is made of steel. And that's the difference between the steel and iron. What are the magnetic materials we know of? Definitely the magnetic materials. We know four magnetic materials. What are the four magnetic materials? Iron, steel, okay, cobalt, and nickel. These are the four magnetic materials we know of. Any other materials would not be magnetic materials. Okay, these magnetic materials we sometimes call them the ferrous. Okay, ferrous materials. Okay, we sometimes call these materials the ferrous materials. Okay, describe a magnetic field as a region. What's a magnetic field? It's a region around. What's a magnetic field? It's a region around a magnet in which other magnets experience a magnetic force. Other magnets will definitely experience some sort of magnetic force, either repulsion or attraction. Okay? Any magnet that enters a field of another magnet will definitely experience some sort of force. Draw the pattern and the direction of magnetic field lines around the bar magnet. Okay, we know how to draw the um, magnetic field around the bar magnet. If this is bar magnet, north and south, okay, north and south, north, good. From the north all the way to the south. No, that the relative strength of the magnetic field is represented by the spacing of the magnetic field lines. If we have these spacings, okay, the distance between these two lines is now a very short distance. That means that this is a strong field. Whenever I increase the distance, such as this means that the field becomes weaker. That the field is becoming much weaker. As I increase the distance between the lines, the magnetic field becomes weaker. And state the direction of the magnetic field at the point as the direction of the force on the North Pole on a magnet. What's this? I mean, this is when we use the compass. When we use a compass, we have a magnet and then north and south. What do we do with the compass? We place the compass at several positions around the magnet. In each position, the compass will point to some certain direction. For example, this compass will point to the left, and this one will also point to the left, while these two will point to the right, indicating that the direction of the magnetic field is going from the north to the south this way. Okay? This is the direction of the magnetic field. It is the direction of the force on the north pole of a magnet, on the north pole of this compass. Where's the north pole of this compass? The pin head, the compass head. This is the north pole of the compass. This is the north pole of this small magnet. The compass is a magnet. Compass is a permanent magnet. Describe the uses of permanent magnets and electromagnets. A permanent magnet could be used as a compass. Okay, we can use, okay, a permanent magnet and a compass. We can use a permanent magnet, for example, in a DC motor. Electromagnets, you can use electromagnets in bells, you know, the electric bells in schools and whatnot. These use electromagnets. Okay, good. Yeah. Electric charge. Okay, one of the easier sessions we had. State that there are positive and negative charges, okay, and that the repulsion forces are between the similar charges, while the attraction forces are between the opposite charges. Okay. Describe simple experiments to show the production of electrostatic charges by friction. Okay, and that this friction causes only the negative charges to move, the electrons. Again, we can have a piece of cloth and a piece of dry cloth and a plastic rod. Okay, cloth and rod, cloth and plastic. hmm, Rod. When I rub the piece of cloth against the plastic rod, what will happen? Electron transfer. So some of the electrons will be transferred from the cloth, for example, to the rod, or vice versa. It depends on whether I say the cloth will become negative or the rod will become negative. If the rod is negative, that means that it has gained electrons from the cloth and the cloth has become positively charged. Or vice versa. If I say that the cloth has become negatively charged, okay, then it has gained electrons from the plastic rod and the plastic rod has become positively charged. Okay. We need to state that the charge is measured in coulombs. Okay. Charge is measured in coulombs. Q is the symbol for the charge. Okay. Symbol for the charge, and the unit of the charge is C, or coulomb. For example, I equals Q over T. Q is the charge, but whenever I measure the charges, 30 coulombs, for example, then I write 30 C. Describe an electric field as a region. What is an electric field? It's the same. It's almost the same idea as the magnetic field. What's the electric field? It's a region around a charge in which other charges will experience, okay, in which other charges experience an electrostatic force. If I have a charge, a positively charged point or whatever, this charge will have a region around it. If I approach another charge, if it's a positively charged, if it's another positive charge, it will repel. If it's a negative charge, it will attract. Why will it attract or why will it repel? Because it has entered the region. Okay, when two charges enter their own regions or the other regions, what happens? Now we call it uh, electrostatic force, either repulsion or attraction. State that the direction of an electric field as a as a point. Okay, at a point is the direction of the force on a positive charge at that point. Again, the direction of the magnetic field. How can I find the direction of the magnetic field? We already know that the direction of the magnetic field from a positive charge, for example, is going outwards, it's moving outwards, but the negative charge is always moving inwards. We know that for a fact. But how did we figure that out? Using another positive charge. We put positive charges inside the field and we looked at how these positive charges moved. If they moved outwards, so this is a positive field, okay, and the positive field has an outward direction. If they moved inwards, then this is a negative field and they have, or the negative field has an inward direction. Describe simple electric field patterns, including around a point charge, okay, around conducting sphere, and between two oppositely charged parallel conducting plates. Again, if I have a point charge, this charge will have, for example, field which is moving this way. صح? Positive charge, it's always outwards. A conducting sphere, for example, if I have a conducting sphere, a positive and a negative sphere, okay, it's going from the positive to the negative. Again, this will be curving this way, okay? They curve around it, okay, this way. That's it. Okay. For example, it could have one of them going outwards كده, one going inwards, outwards, and inwards. You can have some uh, field lines on the opposite side, some field lines هنا, some field lines كده. Okay. These are some of the field lines. Okay. if I have two oppositely charged parallel conducting plates, if I have a positive and a negative plate, then the field lines are always going from the positive to the negative plate. And if you get this question, please try to space the lines evenly. Okay, please try to space the lines evenly. That's it. To show that the electric field is constant throughout the whole plate. That's it. Again, we need to describe and explain to distinguish between electrical conductors and insulators. This is quite easy. A conductor will conduct current. For example, if I have a battery or I connect it to a battery, it will conduct the current. An insulator will not conduct this current. And recall a simple electron model to explain the difference between conductors and insulators. Definitely, we know the difference between conductors and insulators. Conductors have free moving electrons, while insulators do not have these free moving electrons. Okay. Any questions? Okay. Okay. It was one of the easier lessons we had throughout the syllabus, I think. Moving on to the electric current. Electric current is the rate of flow of charge. Rate of flow of charge. Oh. It's the charge passing. We can define it as the charge passing a point per unit time. Rate of flow of charge. That's why I say rate. Rate means a per unit time. I equals Q over T, in which I is the current, Q is the charge, and T is the time. Charge طبعا in coulombs. Charge in coulombs. Time in seconds, and current in amperes. Okay. Describe the use of ammeters. How can we use ammeters, either analog or digital? Quite easy. We can just take the reading from the analog or the digital ammeter. Describe the electrical conduction in metals in terms of the movement of free electrons. Again, we just said that the metals have free moving electrons, and that the particles that move inside the wire are the electrons, not the charges. Okay, the particles that actually move inside the wire are the electrons, not the wires. State that the conventional current is from positive to negative, while the free moving electrons are from the negative to the positive. Okay, this is a point which you tend to forget. If I had a battery, for example, connected to a lamp, okay, this is the positive end and this is the negative end. If I ask you to draw the conventional current, this will be the conventional current, or the current. It's just the current. If I ask you to draw the direction of the electron flow, the electron flow will flow this way. Okay, electron flow from the negative to the positive. But the conventional current, or the current, it always moves from the positive end to the negative end. Okay, definitely the difference between alternating current and direct current. The alternating current moves in two directions. Direct current only moves in one direction. Moves in only one direction. What do I mean by moving in two directions? It means that it's positive, and then it could go into the negative. It could be positive and then go and become negative. That's the whole point of moving in two directions. We have a positive current and we have a negative current. We have a positive current and we have a negative current. A battery, okay, a battery is always a direct current. Battery the only flow of the current inside the battery is only in one direction. It's always from the positive end to the negative end. But the alternating current has to have, okay, this symbol. This symbol is the alternating current. For example, if I had a lamp, okay, this would be an alternating current passing through the lamp. That's it. Any questions?
So if it doesn't have the symbol هادي, it won't be alternating current no matter what. على طول it'll be DC.
If I don't state, okay, if I don't state explicitly that it is an alternating current, then you should assume that it is a direct current. Okay? But if I give you a power source such as this, okay, this is just a power source. This is a power source. At this point, you have no idea whether it's a direct current or an alternating current. He has to state whether it's alternating or direct. That's it.
But what if we get a question that like asks us, how can you tell via diagram if it's alternating or like direct current? How would we know يعني? Like I'm still confused كيف حنفرق بينهم؟
From from the circuit, okay, if you have a circuit, okay, you have to have either this, okay, this symbol which indicates an alternating current, or this symbol which is a battery or a cell which indicates that it's a direct current. If you have a graph, that's a whole other point. If you have a graph could also indicate whether it's direct or alternating. Let me draw a couple of graphs here. Um, for example, if I have a graph like this, okay, this would definitely be an alternating current. صح? This would definitely be an alternating current. Oh, this is the current. It's going from the positive end all the way to the negative end. خلاص يبقى this is an alternating current. Type. What if I had a current moving like this? This would be definitely a direct current. صح? This is a direct current. It's only in the positive end. Type again. If I had something going like this,
Is that direct?
it is direct. It
Okay.
is direct. Why? Because again, it's only on the positive end.
Oh,
صح?
okay.
If I had something going like this, huh,
It's direct.
it's also direct. So this is
Okay.
also a DC current. Okay? Okay. Electrical quantities, voltage, difference between the electromotive force and the potential difference. Okay, we kind of need to memorize the differences now. We kind of need to memorize the difference or the definitions of the electromotive force and the potential difference. What's the electromotive force? It is the work done by a source, work done by a source in moving a unit around a complete sun. In moving a unit what charge? Work done by a source in moving a unit charge. Why? Because we know that the electromotive force is the voltage of the power source. huh? Voltage of the battery, voltage of the alternating, whatever. It's the voltage of the power source. But the potential difference, we know that the potential difference is the voltage of the device. What is the potential difference? It's the work done by a unit charge. This time it's by what? By unit charge passing through a component, passing through a device. Again, voltage done. Okay, it's work done. Okay, and both of them are the work done. Both of them are energies. One of them is work done by the source, and the other one is work done by a charge. When the source does the work, it supplies energy to the circuit. When the charge does the work, it takes energy from the circuit. It takes energy. It uses up energy from the power source. That's the point. That's the difference between an electromotive force and the potential difference. Electromotive force is the voltage supplied to the circuit. Potential difference is the voltage used up by the circuit. You can have a device which uses up, let's say, 12 volts. Okay, so the potential difference of this device is 12 volts. We can have a battery that supplies 12 volts. So the EMF, the electromotive force of this battery is 12 volts. Both of them are measured in volts. Okay, potential difference and electromotive force are measured in volts, but the only difference is one of them is the work done by a source, the other one is the work done by a unit charge. Okay,
Sure. What's work done unit? I forgot.
work done is energy.
So it's joules, right?
Yes, that's why you need to calculate or you need to know how to calculate the voltage. Voltage is equal to the energy divided by the unit charge. Oh, voltage is equal to energy divided by the charge. Both of them
Yeah.
say the same thing على فكرة. E E is voltage. E is stands for EMF. Okay, E stands for EMF and V stands for potential difference. Voltage equals energy over hmm, charge.
Charge.
You divide the energy by the amount of charge you have. Okay. Okay, good. Yeah, moving on. Again, we can use the voltmeters and ammeters. That's quite easy. Resistance. Resistance R equals V over I. R equals V over I. Sketch and explain the current voltage graphs for a resistor and a constant resistance, a filament lamp, and a diode. Okay. A resistor. Okay. Current voltage graph for a resistor. لو constant resistance, filament lamp, and a diode. ماشي. What happens in the constant resistance? Let's talk about the more famous uh, ones, which is the constant resistance and the filament lamp. Constant resistance, it wouldn't matter whether you have VI or IV. If this is VI and هنا V, it would be a constant resistance. It would be a constant slope. Okay, again, if you had VI, would also be a constant slope. I'm talking about talking about the constant resistance. Talking about the constant resistance. But if I had a filament lamp, the problem with the filament lamp is what? The problem with the filament lamp is that it gets hotter with time. Filament lamps get hot with time. As the temperature increases, the voltage increases and the resistance increases. Again, as the temperature increases, the filament lamp has to do with the hmm, temperature. As the temperature increases, the voltage increases and the resistance increases. Therefore, it has to curve towards the voltage axis. Wherever the voltage axis is, yani if this is the voltage axis and this is the current axis, it will curve towards the voltage axis. If the other one, oh, if it was flipped around, this is V and this is I, it will curve upwards. Okay. This is when he says, I want the VI curve for a filament lamp. All good. If you had a constant resistance, okay, constant resistance is a constant slope. Constant resistance, such as um, a resistor, okay, a fixed resistor. Fixed resistor will always have a constant resistor, a resistance in which you have to draw a straight line, and that's it. Okay, and that is it. Hmm. Any questions regarding this part? Hmm. Any questions, Shahab?
Wait, so when we're sketching a diagram for
Hmm.
filament lamp and diode, they're gonna be the same?
لا, diode will be a little different. Okay, diode will be just slightly different than the filament lamp. Okay, slightly different than the filament lamp. Why? Because the diode. Um, do you remember what a diode does? Do you remember
One direction.
one direction? A diode only passes the current through one direction. That's it. Okay, let me sketch a graph for the diode. Let me sketch it here. Okay. Uh-huh. Um, this is okay. The thing with the diode is it passes the current only through one direction. So if it was positive, the current will pass. صح? If it was positive, the current will pass. So let's say this is the V and this is I. Okay? The current will pass, or let's flip them and نخليها I and V. Okay? I and V. But the problem is if it was in the negative direction, it would not pass. So in the negative direction, it has to be zero. Oh, شايفين? Zero on the negative direction. هنا this is all positive. صح? This is positive voltage and this is negative voltage. So on the negative side, it has to be zero. On the positive side, yes, it could. Okay. Oh, it is kind of constant. Okay. Okay, this is the diode. This is the graph for the diode.
Wait,
Hmm.
for the diode, would it ever be the opposite? إنه it's يعني like it goes up and then down? Or like I don't know how to explain it. يعني it
Goes up. لا, the diode always goes up. Okay, the diode is always positive.
okay.
Diode is always positive. Okay. Um. Okay. Describe an experiment to determine the resistance using a voltmeter. Yes, we know how to find the resistance using voltmeter and ammeter. Okay, state qualitatively the relationship between the resistance of metal acquired to its length and its cross-sectional area. Okay, and then again recall and use the following relationships for metallic electrical wire. That the resistance is directly proportional and the resistance is inversely proportional. We know that the resistance is directly proportional to the length. As the length increases, what happens to the as the length increases, the resistance, we know that the resistance increases. As the area increases, what happens to the resistance? The resistance decreases. صح? As the length increases, the resistance increases. As the area increases, the resistance decreases. عشان كده they are inversely proportional, area and the resistance. Okay? As the area increases, it's inversely proportional. And you can use an equation. Okay, it's not that, it's a very simple equation, but you can use one of the, a very simple equation. For the length, if you have the length, you can use a very simple equation, R1 over L1 equals R2 over L2. That's regarding the length, because when the length increases, the resistance will increase. خلاص, it's directly proportional. What about the area? I will have to use an inversely proportional relationship, which is R1 A1 equals R2 A2. R1 A1 equals R2 A2. Why? Because the area is inversely proportional to the resistance. Okay? Okay, حلو. Good. Moving on to the energy and power. One of the easier parts of this lesson. Power equals, we know that power equals IV. We know that energy equals IVT, and then we can define the kilowatt hour. Kilowatt hour is basically the energy. صح? Energy is equal to the power times time. But in this case, the power needs to be in kilowatt and the time needs to be in hours. That's when we measured the energy used in kilowatt hours. To find the cost, we just multiply whatever energy, okay, whatever energy we found in kilowatt hours times the cost per kilowatt hour. For example, if 1 kilowatt hour costs 50 cents, okay, then I'll multiply this energy, the amount of kilowatt hours that I have used, multiplied by 50 cents to find the total amount of money that I should pay. Okay, that's the total cost. It's quite expected to have one of these questions in your test. Okay, it's quite expected. Not all of these. I'm talking specifically about the kilowatt hours. Okay, it's quite expected to have one of these questions in your test. Um, okay, we need to draw some circuit symbols. We know all of these symbols. Cells, batteries, power supplies, generators. How do I draw a generator in a circuit? It's just a box with a G inside it. That's it. Box with a G inside it. G, generator. Okay. Motor. What's a motor? It's M. That's it. Okay. We know the potential divider, the switch, resistor, heater, thermistor, LDR, lamps, ammeters, voltmeters, magnetizing coil. What's a magnetizing coil? It's basically a coil which looks something like this. Okay. That's it. Actually, okay. Actually, we can. Okay. Let me help you out here. We can use the symbols provided here. Okay, take a look at them quite quickly. Okay, these are all the symbols you are required to know. Okay, cell, battery, switch, earth, ground, power supply, DC power supply, AC power supply, lamp, motor, generator, ammeter, voltmeter, diode, LED. Okay, these are all the um, symbols, electrical symbols you are required to know. Okay, that's it.
Sir,
Hmm.
can you explain what a potential divider does?
Can I explain what?
What a potential divider does?
What a potential divider does. Okay. Um, a potential divider, what does it do? It simply divides the potential difference. What do I mean by divides the potential difference? The potential difference of the battery, the voltage provided by the battery, could be divided onto more than one component. Okay, the voltage of the battery, the EMF of the battery could be divided onto one or more component in the circuit. The thing is, okay, the thing is, when you increase the length of this sliding contact, okay, this is sliding contact. This arrow is called a sliding contact. When you increase the length, we know as we increase the length of the wire, the resistance increases. Or if I decrease the length, if I decrease the length of the wire, the resistance also decreases. So the whole point is, if I increase the length, the resistance will increase and the voltage will increase. When I decrease the length, the resistance will decrease and the voltage will decrease. That's it. That's all that has to do with the potential divider.
Wait, sir, whenever it asked me to draw a transformer, I used to do like a box.
لا, okay, actually, when you are required to draw a transformer, you will draw a box with the primary coil and the secondary coil. It's completely right. This
Oh,
is the circuit symbol for a transformer. Probably you will never use this. Okay, probably
okay.
you will never use this circuit symbol. Why? Because up till now we don't have any circuits that have that have transformers in them. Okay, up to now, we don't have any circuits that have transformers in them. So you will not be needing to draw the circuit symbol for the transformer.
Sir, معلش, what's a relay coil and a magnetizing coil? بس يعني آخر شيء I don't know.
Okay. A relay coil, a relay, I will explain a relay and how it uses a magnetizing coil in a bit. Okay. I will explain the relay inshallah. Um, okay. How we draw the box one. What's the box one? You mean the transformer? Okay, again, when I get to the transformers, we will learn how to draw a transformer. It's a very easy drawing. We all know it. Maybe you've forgotten it now, but we know how to draw it. Okay, when I get to the transformers. Okay, let's get back to where we stopped.
Wait, Mr.
Hmm.
Is the relay coil the thing about fire alarm or something?
Yes, some fire alarms do have relay coils. Yes. Okay. Okay. So these are some of the drawings that we are required to do. Series and parallel. Okay, we know that the series has the same current. Okay, the current is the same. We know that in a parallel circuit, the sum of the currents entering a junction is equal to the sum of the currents that leave the junction. It's quite easy. Again, if I have a parallel circuit, if I have a parallel circuit, for example, the whole point is if I have هنا 10 amperes and this lamp receives 3 amperes, so definitely the other lamp has to receive 7 amperes. That's the whole point of this point A. Total potential difference across the components in a series is equal to the sum of the individual potential differences across each component. Again, if I have a battery and I have two components, for example, or if I have three components, whatever, and this battery is 24 volts, if the first lamp has a voltage or has a potential difference of 12 volts, then the other one will have 12 volts. Okay, instead of writing down 12 volts, let's write down 18 volts. So the other one will have a voltage of, or a potential difference of 6 volts. صح؟ This is series and parallels, very simple. The potential difference across arrangement of parallel resistances is the same. Yes, we do know if we have a parallel circuit and this battery is 12 volts, then the potential difference of this lamp will be 12 volts and the potential difference of the other lamp will be 12 volts. Very basic knowledge, okay? Very basic knowledge. Again, if you've forgotten any of these, please tell me now. Okay?
Wait, sir, in a parallel circuit, what's always the same? The current?
In a parallel circuit, no, the voltage
The
is the same.
resistance? Oh, voltage. Okay.
Okay?
Oh, it's this point, the one you just said?
Yeah. Okay. Know how to construct and use series and parallel circuits. How to use series and parallel circuits, okay, we know them. Calculate the combined EMF of several, okay, we've done that, 18 plus 6, okay. EMF of several sources in series, combined resistance of two or more sources in series. Again, if I have 3 or 4 resistors in series, I just add them up, okay. We just add them up with summation. We just add them up. State that for a parallel circuit, the current from the source is larger. Okay, definitely the current from the source, so 10 amperes, is larger than any of the other branches. صح? State that the combined resistance of the resistors, of two resistors in parallel, is less than either resistor by itself. Again, this is quite simple. If I had two resistors, if I had, let's say, two resistors, 3 ohms and 6 ohms. We already know that the total resistance has to be, okay, the total resistance has to be less than 3. Has to be less than 3. We can calculate it. Yes, we can calculate the combined resistance. We know product, okay, product over sum. Product over sum, 6 times 3 over 6 plus 3, which would give me a total of 2 ohms. يبقى the combined resistance of these two resistors is 2 ohms, which was definitely less than 3. So we're not wrong. Explain the sum of two currents in a junction is the same as the sum of currents outside the junction. خلاص, we did that in the parallel circuit above. State the advantages of connecting lamps in parallel. We know the advantages of connecting lamps in parallel. So we have 3 advantages. What are they? Okay, what are the 3 advantages? Same voltage. Okay, they all have the same potential difference or same voltage. If one lamp breaks, if one lamp breaks, the others are not affected. The others are not affected. Okay. And last but not least, we can switch on and off. Okay. We can switch each one on and off independently. That's why we construct parallel circuits, because we can have the same voltage. One of them breaks, the others wouldn't be affected. Why is the same voltage an advantage? Okay, why is the same voltage an advantage? Because now when I am building a new appliance. For example, I'm building a new laptop or a new television set or whatever. It's much easier for me to construct this laptop or television or whatever with the specs, with the same specs. I mean, it will have a voltage of 230 volts. All of my appliances will have the same voltage. Okay. If one of them needs only 20 volts and the other needs 50 volts and one needs 70 volts, this would be too much of a hassle. So yes, it is an advantage for the parallel circuits to give off the same voltage for all of the components. Why? Because we can just build them all with the same specs and يعني, uh, and avoid the hassle. Okay. um ماشي يلا. Know that the potential difference, yeah, know that the potential difference across an electrical conductor increases as the resistance increases. Yes, we know that as the resistance increases, the voltage also increases. Yeah. Potential divider, what does a potential divider do? Potential divider, it divides literally divides the uh, potential difference. It divides the voltage onto the um, different devices we have. We can use, okay, we can use a ratio R1 over R2 equals V1 over V2, or you can use it in another way, which is V1 over R1 equals V2 over R2. It's the same. It's the same. Okay. What's this? It has to do with dividing the voltage. For example, if you remember, okay, we had many questions regarding this point. We had many questions regarding this point. For example, if I had a battery and two resistors in series. This battery had a voltage of 36 volts. And for example, this resistance 2 ohms and the other resistance was 4 ohms. The potential difference states that, or the potential divider states that the voltage 36 volts will be divided onto each of these resistors, okay, proportionally. What do I mean proportionally? I had 2 ohms and the other one was 4 ohms. The total combined resistance of them both is 6 ohms. The total voltage is what is 36 volts. So we can easily cross multiply. You can easily cross multiply. So for example, 4 times 36 divided by 6 is 24 volts. So the 4 ohm resistor will receive 24 volts. 2 times 36 divided by 6 is 12 volts. So the 2 ohm resistor will receive 12 volts of potential difference. Okay, 12 volts. This هو ده, it's the concept of a potential divider. Okay. Okay, يلا. Some safeties, some electrical safeties and some hazards. What are some hazards that we have? Damaged insulation. Okay, damaged insulation could cause an electric shock. Damaged insulation could cause an electric shock. Overheating could cause a fire. Damp conditions could cause an electric shock. Excess current could cause a fire or could cause electric heating. Okay, or overheating, I mean. No, that the main circuit consists of live wire, neutral wire, and an earth wire. We have 3 wires in any electric circuit, especially if there is a metal casing. Okay, if there is a metal casing, we have to have these 3 wires. For example, if I had a dishwasher, okay, this is a dishwasher. The dishwasher has a metal casing. Metal casing. We have 2 wires in the dishwasher. These 2 wires are the positive end and the negative end. Instead of naming it the positive end, we name it the live wire. Instead of naming it the negative end, we call it the neutral wire. Live wire is the positive, neutral wire is the negative. But what about the earth wire? Earth wire is literally just a wire connected to the earth. Literally, we just connect this wire from the metal casing to the ground. That's it. Sometimes we call it grounding or ground wire. Okay. What does this wire do? It protects the user from an electric shock. How does it protect the user from an electric shock? If for some reason the live wire touches the metal casing, if for some reason the live wire touches the metal casing, what happens? The metal casing will become live. The metal casing would, for example, electrocute us. But how can we prevent electrocution? What do we do? All we do is we earth or we ground this metal casing. When we ground this metal casing, all of the electrons of the excess current will pass all the way to the ground. Okay. That's it. Okay, that is it. That's why we use an earth wire. Okay, why do we use a fuse? Or how do we connect a fuse in um how do we connect a fuse in a circuit? Okay, for example, the live wire has to have the switch, and then on the live wire there is the fuse. Oh, there's a fuse on the live wire, which is also connected again back to the neutral wire. Why do we put the fuse on the live wire? To protect the circuit from overheating. When the current increases, what does the fuse do? The fuse melts. The fuse melts, protecting the circuit or protecting the device from overheating or protecting the device from any damage. So this is what the fuse does. Um, Again, explain why the outer casing of an electrical appliance must be either non-conducting or earth. Either non-conducting or or earth. Again, if it's earth, خلاص احنا we know why it's earth, to protect the users from any electric shock. If it's non-conducting, if it is non-conducting, then it will not conduct any current. If the live wire touches, so if the live wire touches the casing, and the casing is not a metal, if it's a plastic casing or whatever, will I get electrocuted? No. No, why? Because um it's not a conductor. It's an insulator. Again, state what the fuse does. خلاص احنا we said what the fuse does. Any questions?
Wait, yeah, I kind of didn't get it.
Okay. ايه المشكلة؟
So it goes to live and neutral. It goes to live and neutral, but like I don't get what the difference between live and neutral is.
Um, live basically is the positive end of the wire and neutral is the negative end of the wire. That's it. That's the whole point. يعني
في
هو
سؤال هيسألنا عنهم؟ لا صح؟
لا لا لا. Live is the positive. هو the question is يعني one of the questions could be on which wire do we attach the fuse, for example. Okay, the fuse has to be on the live wire.
Oh, okay. So the fuse is on the live wire.
Has to be on the live wire. The fuse has to be on the live wire and in series. It has to be in series on the live wire. Okay. Any questions?
Yes, thank you.
Okay, you're welcome. Um, okay, yeah, moving on to the next question.
Wait, actually, I have this one. Is it live and neutral? Is that the same as the Earth? لا صح.
لا لا ما I said the Earth is a third wire. Earth
Yeah, it's
is
the third one that's above them, صح?
no, it's totally different. It doesn't have to be above or below. It's totally different. It's a whole
Oh.
other wire.
But it just goes to the ground, right?
It goes to the ground. Okay?
Okay.
It goes to the ground. Okay? This is the earth wire. Okay?
Okay.
Okay. Um, يلا. Moving on. Electromagnetic effects. Electromagnetic induction. First of all, we need to talk about the generator, and then we will move on to the finish up the generator first, and then we will move on to the electric motor or DC motor. What's a generator? Induction. Induction means that we are producing a current. صح? Electromagnetic induction. It means ايه? It means that I am producing some current. No, that a conductor moving across a magnetic field for changing magnetic field linking conductor can induce EMF. Can, okay, so sorry. Again, no, that conductor moving across a magnetic field or changing magnetic field. Okay, conductor moving across a magnetic field or a changing magnetic field could induce an EMF. How could it induce an EMF? Okay, very simply, if I had a north end and a south end, okay, north pole and a south pole, and I had a wire inside this pole, and it was connected to a galvanometer. What will happen if I move this wire up and down? If I move this wire up and down, what will happen? All that will happen is that it will produce an induced current. صح? This wire will cut the magnetic field. صح? This wire will cut the magnetic field. When it cuts the magnetic field, it induces a current. Okay? When it cuts the magnetic field, it induces a current. And that's it. Okay? Describe an experiment to demonstrate the electromagnetic induction. We can either use this one, or there's another experiment to demonstrate electromagnetic induction in which we had the galvanometer attached to coil, and then north and south we had another magnet, and this magnet was moving towards the coil. Whenever this magnet moves towards the coil, what happens? You tell me, wallahi, when the magnet moves towards the coil, the magnetic field lines of the magnet cut. Okay, the magnetic field lines of the magnet, what do? They cut the coil. Whenever they cut the coil, what happens? An induced current is produced inside the coil. So, an induced current is produced inside the. That's it. صح? That is it. طيب. Um, know that the direction of an induced EMF opposes the change causing it. Again, direction of an induced EMF opposes the change causing it. What do I mean by this statement? If I have a magnet moving towards the coil in this direction, okay, moving towards the coil in this direction, then the coil will become an electromagnet. Okay, the coil will become a magnet in this instant, but the magnetic field of this coil will have a north pole on this side and a south pole on the opposite side. Again, it will have a north pole on this side and the south pole on the opposite side. When it's moving to the left, what happens if it's moving to the right? What happens if it's moving to the right? The poles will be switched. The poles will be flipped. That's it. Okay, that is it. Again, this is what he means by that the direction of an induced EMF opposes the change causing it. It opposes the change causing it. Yani it's the opposite. Okay? طيب. State and use the relative directions of force and field induced current. Okay, North Pole and the South Pole. State the factors affecting the magnitude of an induced EMF. What are the factors affecting the magnitude of an induced EMF? We know the factors affecting, we have three factors. What are they? The speed of the motion, speed of the rotation. We have the strength of the magnetic field, and we have the number of turns in the coil. صح? Three factors which affect the strength of the magnetic field. Okay. Any questions? I know this part might be a bit tricky. Might be a little tricky. AC generator. What's an AC generator? Describe a simple form of AC generator, rotating coil or rotating magnet. Okay. Then use the slip rings. You have to use slip rings in an AC generator. You have to have slip rings. I can modify this drawing. Okay. I can modify this drawing by having a north pole on this side, a south pole on the other side, and a coil inside the magnetic field. This coil is attached to some slip rings. Again, slip rings. These are slip rings, which are connected to a galvanometer. Okay. Whenever you have a galvanometer, then you know that this is an AC generator. Okay. Um, the graph of the EMF against time, whenever you have a generator, it produces what? It produces an alternating current. That's why we name it the AC generator. It produces an alternating current. It keeps on moving up and down, up and down, alternating current. The graph of the generator will always be كده. Definitely current or voltage. It will always be an alternating current. Okay. The point at which there is a peak and the point at which there is a zero. It has to do with what? It has to do with the coil itself. If the coil, for example, at this instance is moving upwards, okay? What happens to the coil? It keeps on moving in a complete rotation. If it's moving upwards at this instant, then it's producing the maximum voltage or the minimum voltage. It's the same. What do I mean by maximum or minimum? I mean maximum amplitude or the minimum amplitude. They're the same. Maximum amplitude or the minimum amplitude. After a while, the coil will become horizontal. When it's moving horizontally this way, it's moving with the magnetic field lines. And when the coil moves along the magnetic field lines, what happens? تقولوا لي zero output. No voltage will be produced. صح? When it's moving horizontally, then no voltage will be produced. Why? Because it's moving with the magnetic field. It's not cutting the magnetic field. Okay? It is not cutting the magnetic field. It's moving with the magnetic field. خلاص؟ يبقى again, north pole, south pole. If I'm moving up or down, I'm cutting the magnetic field perpendicularly, so I will produce the largest magnitude. If I'm moving left or right, I will produce the least amount, which is zero when I'm moving horizontally. Okay?
Wait, sir, what was the sentence? You know the one حقت الترانسفورمرز نفسه
Yeah.
اللي هي cutting. Can you write it, please?
When we get to the transformers, I will write it. Don't worry. Okay. You mean that when the current, when the coil or when the wire cuts the magnetic field, it produces an induced current. صح?
Yeah,
That's
that's one.
when the wire cuts the magnetic field, an induced current is generated, or it produces an induced current inside the coil or inside the wire. Okay? Okay.
wait هو احنا هنا مش بنقول perpendicularly صح؟ مش زي ال DC صح ولا؟ لكن the wire cuts perpendicularly to the magnetic field so it produces an induced EMF.
Yeah, when
Like,
it cuts perpendicularly.
okay.
Okay. You don't have to say perpendicularly, but you have to know that it is perpendicular cutting. Okay. Because if it's moving horizontally or parallel to the line, it's not cutting the line. If it's moving horizontally, it wouldn't be cutting the magnetic fields. It would be just moving along the magnetic fields. Okay. Magnetic effect of a current. Describe the pattern and the direction of the magnetic field due to currents in the straight wires and solenoids. Okay. If we had a wire moving into the page or out of the page, okay, into the page or out of the page. If you remember, into the page was an X. And how do we draw the magnetic field into the page using the right hand rule grip? So it will rotate in a clockwise motion. And then you had two circles which were close together, and then a third one which was a bit further apart. Okay, so into the page would be clockwise. Out of the page was a dot. It would have been anti-clockwise. Out of the page. Definitely when you're drawing these circles, draw them using a compass. Don't draw them using your hands. Okay, out of the page. Of the page. This is an anti-clockwise rotation. Using the right hand rule grip. Okay. Um, solenoids. Solenoids. How is the magnetic field generated inside the solenoid? If this is a solenoid, in the center of the solenoid, the magnetic field lines are straight. Okay. In the center of the solenoid, they are straight. Outside the solenoid, what happens is that they start to curve this way. Okay. You can draw some loops outside the coil. No, outside the coil, loops just like this. Inside the coil, straight lines. Outside the coil, loops. ماشي. Describe and explain to identify the pattern of the magnetic field. Okay. Describe how the magnetic effect of a current is used in relays. Relays. What is a relay? Very simply put, a relay. Where can I draw it? Okay, let me draw the relay here now. What is a relay? For example, I could have a small circuit on the left-hand side with a battery, okay, and a thermistor, okay, and a magnetic coil. This is a magnetic coil. The magnetic coil is right next to a switch, an iron switch. The magnetic coil is right next to an iron switch. And then on this side, we have, let's say we have a lamp and an alternating current or an alternating power source of 230 volts. Okay, and this is also connected to a bell. Okay, it's connected to a bell. And this side, it's only 5 volts. What's a relay? What is a relay? A relay, very simply put, okay, uses the magnetic effect. Uses what? The magnetic effect. Where's the relay in this circuit? This part is called the relay. Okay. This is what I call a relay. What does this relay do? This is actually a circuit for a fire alarm. This is a very simple circuit for a fire alarm. What does it do? We have on the left-hand side a thermistor. When the temperature increases, what happens to the um, when the temperature increases, what happens to the resistance? Resistance decreases. That when the resistance decreases, what happens to the current? The current increases. Okay, so when you have an increased current in the magnetic coil, when you have an increased current in the magnetic coil, what happens? You'll have a stronger magnetic field. Okay, you'll have what? A stronger magnetic field. What does this magnetic field do? It attracts. What does this magnetic field do, huh? It attracts the switch. Therefore, the opposite circuit or the other circuit, what will happen to the other circuit? It will be closed. The current will now pass in the other circuit. the lamp will be switched on, the bell will ring, and everything will be switched on in the other circuit. Again, what happened? Did you, as a human, interfere with the second circuit? No. We didn't touch it. We didn't do anything to the other circuit. Okay? And that's the point of a relay. A relay uses a small circuit current, which is on the left-hand side, to switch on a large circuit current, such as the 230 volts uh, alternating current. Again, what does a relay do? It uses the magnetic effect. It uses what? The magnetic effect to switch on a large circuit using a small circuit. To switch on a large current using a what? A small current. That's it. That's it. That's the whole method of operation of a relay. A relay, what does it do? It uses magnetic effect to switch on a larger current using a very small current. That's it.
Sir, I'm so sorry, but can you write the sentence? Because I feel like I'm gonna.
Okay, okay. Um, I'll write it down here. What does a relay do? Uses, okay, uses the magnetic effect to switch on, to switch on a large current, okay, switch on a large current circuit using a small current circuit. Okay. اوكي حلو. اوكي يس. um خلاص are you done?
Yeah.
Okay. Okay. State qualitative variation of the strength of the magnetic field around the straight wires and the solenoids. Okay, again, they increase with the current. Once the current increases, the magnetic field does increase around a wire or around a solenoid. Okay, describe the effect of the magnetic field around the straight wire and solenoid changing the magnitude and the direction of the current. If you change the direction of the current, then definitely the direction will be in the opposite. For example, if you change the direction of the straight wire, instead of being into the page, it becomes out of the page, then instead of the loops being clockwise, they will be anti-clockwise. That's it. Okay. Okay, يلا moving on. DC motors. Force on a current carrying conductor. DC motors. Describe an experiment to show that the force acts on a current carrying conductor in magnetic field, including the effect of reversing the current and the direction of the field. If I have a simple motor, north end and the south end, and then I have a wire connected to a battery. Okay, I have a wire connected to a battery. This wire has a current moving this way. Okay, this is the current inside the wire. And then I have the magnetic field, north to south. Magnetic field, north to the south. We can use the Fleming left-hand rule. We can use the Fleming left-hand rule to indicate in which direction will this wire move. Using the Fleming left-hand rule quite quickly would indicate that this wire would move out of the page. Out of the page. What would happen if I reverse the current? The wire would move into the page. What would happen if I reverse the magnetic field? The wire would also move into the page. What will happen if I reverse both? What will happen if I reverse the current and the direction of the magnetic field? The wire will remain out of the page. Oh, it would still move out of the page. Okay. Again, what happens is that the current interferes with the magnetic field at 90 degrees. They have to be perpendicular, and therefore the force will also be perpendicular to them both. That's why we use the Fleming left-hand rule. Okay? Directions of the force, magnetic field, and the current. Fleming left-hand rule. left-hand rule. Determine the direction of the force of beams. Okay, charged particles. Charged particles in a magnetic field. Usually we used to explain this part with the atomic physics. Okay, with the atomic physics. If I have a beam of charged particles, either alpha or beta. Okay, either alpha or beta. let يعني we'll explain this. Okay, we'll explain this part when we get to the atomic physics إن شاء الله. يلا DC motor. Yeah, quickly. A DC motor, what does a DC motor, or how can we control the speed of the DC motor? Okay. If I want to increase the speed of the DC motor, I need to increase the number of turns, I need to increase the current, and I need to increase the magnetic field. Okay. Describe the operation of the electric motor, including the split ring commutator. What does the split ring commutator do? It's very important to remember. What does the split ring commutator do? It reverses what? Reverses the current every half يلا every half rotation to keep the coil rotating in one direction. Okay, in one direction. That's the um okay, that's the operation of the um split ring commutator. It's very crucial. Okay, without the split ring commutator, without the split ring commutator, the wire or the coil would keep on rotating half a rotation to one side and then half a rotation to the other side, half rotation to one side and then half rotation to the other side. If you didn't have the split ring commutator, but due to the split ring commutator, it keeps on rotating in the same direction for as long as you have the current in the wire. Okay. Okay. Yeah. Transformers, last part in unit 4. Transformers. Describe transformers was rather easy, alhamdulillah. Describe the construction of a transformer. How do we draw a transformer? We simply draw a iron core, an iron core. I have an iron core, and then I have the primary coil on the left-hand side and the secondary coil on the right-hand side. This has to be an iron core. And these have to be the primary coils and the primary and secondary coils. Okay? What's the difference between a step-up transformer and a step-down transformer? Step-up transformer increases the voltage in the secondary coil. Step-down transformer decreases the voltage in the secondary coil. This has to do with the equation Vp over Vs equals Np over Ns. Again, you can use this equation in a different way. You can use it, for example, Vp over Np equals Vs over Ns. Okay, there are many different ways in which you can write down this equation. Let's write down the principle of operation of a transformer, of an iron core transformer. The principle of operation of an iron core transformer. How does it work? Okay. The input voltage, the primary voltage has to be AC. Primary voltage has to be AC. And the secondary voltage will be AC. But the input, the primary voltage, it must be an alternating current. Why? Why so? The alternating current, okay, the alternating current in the primary coil creates an alternating magnetic field. Okay, an alternating magnetic field. Again, the alternating current in the primary coil creates an alternating magnetic field, which cuts or which keeps on cutting. Okay, which cuts. This is a very important key word in this question. Okay, which cuts what? The secondary coil. Which cuts the secondary coil, producing an induced alternating current. Okay, an induced alternating current. That's it. This is the method of operation. This is how the transformer works. Okay, this is how the transformer works. Alternating current in the primary coil creates what? An alternating magnetic field. This alternating magnetic field cuts the secondary coil. When it cuts the secondary coil, it produces an induced alternating current. Okay, produces current. Yes, it does produce a current, but this produced current, this secondary current, this output voltage, this output, it has to also be alternating. What happens if we use a DC input? It will produce an alternating current, but just for a split second. Just for a split second. And then it will go back to zero. Why? Because the DC current does not produce an alternating magnetic field. It will produce a magnetic field, but this magnetic field is constant. This magnetic field does not change. This magnetic field doesn't keep on cutting the secondary coil. This magnetic field, doesn't keep on cutting the secondary coil. If it doesn't keep on cutting the secondary coil, then it wouldn't produce any current. Okay, for the current to be produced, for the current to be induced, you have to have some sort of motion, some sort of cutting, some sort of constant cutting. Okay, so the primary coil has to have an alternating current in it.
لا I have a question. يعني في الباس paper مثلا لو جه قال لنا يعني in general قال لنا إن it's a DC motor DC like motor transformer وإن إحنا يعني بيبقى دايما it's like a two marker and it tells us if it's a DC what would like change أو we'd have to explain it. Don't I say إن في primary coil it would be DC and then it would only like cut like for a brief time and the galvanometer would deflect and then go back على طول.
Yeah.
صح؟
Yeah,
يعني
you will say this. It will produce a current for a split second, for a very brief time, and then it will go back to zero. That's it.
that's it.
Okay. طيب, good. حلو. We have another equation to find the current. IPVP equals ISVS, which relates the current to the voltage. And in this equation, we can see that the current is inversely proportional. Inversely proportional, which is a good thing. Which is a good thing that the current is inversely proportional. Why? Because one of the advantages of high voltage transmission is that as the voltage increases, the current decreases. This is an advantage. This is an advantage. Yes. Why? When the current decreases, the heating effect in the wire decreases. Okay. And the power losses in the cables are smaller. Okay. Again, when the current increases, when the voltage increases, the current decreases. Oh, current decreases. Current decreases. So the heating effect, also decreases. When the heating effect decreases, the power lost decreases. Okay, because P equals I squared R. P equals I squared R. When you decrease the current, the power lost will decrease a lot. ماشي. Describe the use of transformer in high voltage transmission. Yes, we have to transmit electricity using very, very high voltages to prevent, or not to prevent, to decrease the amount of energy lost, to decrease the amount of power lost. Okay, due to the heating effect. Okay. Any questions? Any questions regarding the transformers or Unit 4? كده الحمد لله we finished up Unit 4.
أنا بس I have a question. هو إحنا just to make sure هو إحنا when do we use ال Fleming left hand rule
Fleming
Like,
left-hand rule is used with the motor, with a DC motor. Fleming right-hand rule is used with an AC generator. AC generator and DC motor, we both use one of these rules. Generator, right-hand rule, Fleming right-hand rule. DC motor, Fleming left-hand rule. If you have a galvanometer, if you have an induced current, galvanometer or induced current, they will indicate, or this is an indication of, okay, this is an indication of Fleming right-hand rule, or that this is a generator. If you have a battery, or if you have a current carrying wire, then this is an indication of a DC motor. Okay? That's it. It's as simple as that. All good?
thank you.
Okay, حلو. Okay. كده we finished up unit 4. الحمد لله. Unit 5, nuclear physics. Nuclear physics was a bit easy, to be honest. Okay. Part of it was very easy. Part of it had to do with chemistry, the structure of an atom, protons, neutrons, nucleus, electrons. This was the easy part. And there was a slightly harder part. Okay. Let's discuss them quite quickly. Describe the structure of an atom in terms of positively charged nucleus and negatively charged electrons. Okay, we have a nucleus with some electrons around it. Okay, this is quite easy. Okay, know how the atoms may form positive ions by losing electrons or negative ions by gaining electrons. Okay, this is quite easy. Describe the scattering of alpha particles, okay, by a sheet of thin metal supports the nuclear model of the atom. The scattering, Tadi, experiment, okay, what did we learn from this scattering experiment? We learned three things, okay? We learned three things. First of all, for example, if this was the nucleus, okay, these were the nuclei of the um, metal, of the thin metal. Most of the alpha particles passed without any deflection. Most of the alpha particles passed without any deflection. So we learned what? That there is a very small nucleus, or that the atom is mostly empty. Okay? The atom is mostly empty because 99% of the alpha particles passed without deflecting at all. Then some of the alpha particles deflected with almost a 180-degree deflection. Some of the alpha particles hit and then rebounded back. When they rebound back, this means what? This means that there is a mass, there is a heavy object in the center. There is a heavy object in the center. This heavy object contains the mass, all of the mass of the atom is inside this object, which we named later on the nucleus. We also found that some of the alpha particles, let me draw it in another color. Okay, some of the alpha particles, as they approached, deflected with some angle. Okay, some of them deflected upwards and some of them deflected downwards. Okay, why? Because they found out, or we found out eventually, that the nucleus was also positively charged. So we learned three things. The atom is mostly empty. The atom is mostly empty space. Um, all of the mass, all of the mass of the atom is inside the nucleus. Okay, and the nucleus is positively charged. That's why some of the uh, alpha particles were deflected with some angles.
Wait, I don't get why if it's deflected, that means it's positive.
Uh, why would it change its direction if it isn't repelled? يعني think about it.
it's like 2 alpha particles.
Yes, not two alpha particles, but you have a positively charged particle and another positively charged particle. What will happen? They will repel each other. So now the
So
alpha
we
particle
can-
is going towards, or not towards, near, it's moving near the positively charged nucleus. So if it's approaching near the positively charged nucleus, it will deflect, it will repel. That's why it moves with a certain angle upwards or downwards.
So how do we know the thing it's moving towards if it's positive or negative?
لا, we know that the alpha is positively charged. That's
Not
something.
the alpha, not the alpha, the other one.
The nucleus, okay, if it was negatively charged, okay, if it was negatively charged, it wouldn't have moved away. It would have been attracted towards the
Yeah.
nucleus. صح?
So that's how we know it's
That's
positive.
how we know it's positive.
Okay.
Okay, good. The nucleus, we know that the nucleus contains the protons and the neutrons. Okay, and we need to state the relative charges of protons and neutrons, definitely positive 1, neutron 0, and electron negative 1. Define the term proton number or the atomic number as Z, the mass number as A, okay, and the number of neutrons. To find the number of neutrons, we must, in physics, we must use this nuclide notation. We have to use this nuclide notation. For example, if I had carbon, okay, carbon has 6 protons and 6 neutrons. So the atomic number of carbon would be 6. The nucleon number or the mass number of carbon would be 12. We must use this nuclide notation. What's the difference between carbon 12 and carbon, for example, 14? Okay, they are both the same element, but they are different isotopes. They are different isotopes. The same element, but different isotopes. They have the same number of protons, but different number of nucleons or neutrons. That's what makes it an isotope. So isotopes are basically the same element with different number of neutrons or different number of mass nucleons or whatever. Describe describe the process of nuclear fission. What is fission and fusion? The difference between fission and fusion. Fission is the splitting of, okay, fission is what يا شباب? Fission is the splitting of atoms, of large atoms such as the uranium. Fusion is the joining of smaller atoms such as hydrogen. We join 2 hydrogen atoms to produce a helium atom. Okay, fission, splitting, joining, fusion. Both of these processes give off huge amounts of energy. Both of these processes give off huge amounts of energies. No, the relationship between the proton number and the relative charge on the nucleus. The relationship between the proton number and the relative charge on the nucleus is positively charged. For example, if I talk about the nucleus, if I'm talking about the nucleus of the carbon, if I'm talking about the nucleus of the carbon, the nucleus of the carbon has a positive charge of 6. I'm only talking about the nucleus of the carbon. The nucleus of the carbon is positively charged, okay, plus 6. What
We
about
won't
the whole
agree.
atom? If I'm talking about the whole atom, it has a neutral charge. The whole atom has a neutral charge. Why? Because the number of protons are equal to the number of electrons. But inside the nucleus, you don't have any electrons. Inside the nucleus, you only have protons and neutrons. Therefore, if I ask you, what is the relative charge of the nucleus, okay, of the nucleus alone, you will always say the relative charge of the nucleus alone is the number of protons inside that nucleus. And that's it. Okay? No, the relationship between the nuclear number and the relative mass. Okay, again, the nuclear number is the mass of the nucleus. It is the mass of the nucleus. حلو. يلا. Detection of radioactivity. Okay, could you repeat the last part? Yes, I can repeat the last part. Which one? Part 7 or 8? If I'm talking about the nucleus, if I'm talking about the nucleus of the atom, okay, for example, nucleus of the carbon, Okay, it has 6 protons and, let's say, if I'm talking about carbon 12, and 6 neutrons. And then it has 6 electrons in the electron shell or the electron cloud. If I'm talking about the carbon as a whole, the carbon atom as a whole, the relative charge of the carbon atom as a whole is 0. Why? Because the number of protons are equal to the number of neutrons. I'm sorry, number of protons are equal to the number of electrons. Okay, if I'm talking about the carbon atom as a whole. If I'm talking about the carbon nucleus, the nucleus by itself is positively charged. Why? Because you do not have any electrons inside the nucleus. We have no electrons inside the nucleus. So if you have no electrons, then if you have a positive charge, it will be positively charged. It will be definitely positively charged inside the nucleus. That's it. Okay. I hope you got that part. Okay. Detection of radioactivity. We have something called the background radiation, random background radiation. What's the random background radiation? What are some of the main sources of the random background radiation? Radon gas, rocks and buildings, food and drink. صح? Cosmic rays, cosmic rays. The sun. We have several sources of random background radiation. Okay. We have a detector to detect this radiation. It's called the GM tube. صح? It's called the GM tube. This is the detector that detects the radiation around us. Use count rate measured in counts per second. Okay, counts per second or counts per minute. Use measurements of the background radiation to determine the corrected count rate. Yes, we know how to find the corrected count rate. For example, if I have the background radiation is 30 counts per minute, and then I bring in the uranium or whatever, and the detector reads 570 counts per minute. Counts per minute. Okay. Then to find the uranium alone, we have to subtract 570 minus 30 would be 540. So the uranium on its own is 540, or it's giving off a radiation of 540 counts per minute. Why? Because you have to subtract the background radiation first. Okay. Describe the emission, okay, of radiation from a nucleus as spontaneous and random. What do I mean by spontaneous and random? Again, random and spontaneous, it means that there are no factors that affect the count rate. There are no factors that increase the count rate or decrease the count rate. You can never say for sure that this specific atom will decay at this specific time. No, you have no idea. Okay, it's random and spontaneous. Okay, it cannot be affected by any external factors. It cannot be affected by the weather. It cannot be affected by the time of day. It cannot be affected by the season. Okay, it's not affected by any external factors. So definitely, any radiation has to be random and spontaneous. We know the 3 types of radiations being emitted by unstable isotopes. We have 3 types: alpha, beta, and gamma. Alpha, beta, and gamma. We need to know their nature, the ionizing effects, and the relative penetrating abilities. Yes, we know the natures. What's the nature of an alpha? An alpha, okay, quite quickly, an alpha is a helium nucleus. A helium nucleus. If you say it's a helium atom, that's wrong. If you say that the alpha is a helium atom, that is wrong. It's only a helium nucleus. Okay? Because it doesn't have any electrons. It does not have any electrons. What about the beta? The beta is basically an electron, a negatively charged electron. And the gamma is an electromagnetic radiation. Electromagnetic radiation. It's a wave. It has the speed of light, 3 times 10 to the power of 8 meters per second. The relative ionizing effects. The alpha has the strongest ionizing effect. beta is weaker, gamma is the weakest. Alpha has the strongest relative ionizing effect. Why? Because it has a charge of +2. +2. So it's very strongly ionizing. An electron only has a charge of -1, or the beta only has a charge of -1, and the gamma has a charge of 0. So the relative ionizing effect of the alpha is the strongest, then the beta, then the gamma. If we want to talk about the penetrating abilities, the alpha is the weakest. Then comes the beta, then comes the gamma. The alpha can be stopped by a thin sheet of paper. Beta can be stopped by a thick sheet of aluminum, and the gamma can be stopped by or reduced by a thick lead wall or a thick concrete wall. صح؟ Um,
So the most penetrating is gamma.
yes,
But
definitely.
is it the least ionizing or the most ionizing?
Yes, least ionizing. So the most penetrating is the least ionizing, and the least ionizing, and the most ionizing, the least penetrating.
So alpha is most ionizing, least penetrating, and then
Yes.
gamma is that. But what about beta? It's just like, what do we say? It just
Beta is it has a medium يعني
it says beta particle not included. Never mind.
okay, beta particles. Okay. لا, beta particles are included.
Yeah, it says the relative penetrating abilities, beta particles are not included.
Relative penetrating ability, it's stronger than the alpha, but weaker than the
Gamma.
gamma. That's what you need to know. Okay. Okay. Describe the deflection of alpha particles, beta particles, and gamma radiation in electric fields and magnetic. Yes.
What did you say they're stopped by?
Alpha is stopped by a sheet of paper. Beta is stopped by a thick sheet of aluminum. And gamma is stopped by a thick lead wall or concrete wall.
Okay.
Okay? طيب. Let's discuss alpha, beta, and gamma while moving through an electric field and while moving through a magnetic field. The simplest one is the electric field. If I have a positive field, okay, positive plate and a negative plate. Okay, I have alpha, beta, and gamma. Alpha, beta, and gamma. The alpha is positively charged. It is positively charged. So basically, the alpha will be attracted to the negative plate. That's quite easy, quite simple. The beta is negatively charged. So definitely it will be attracted to the positive plate with a strong deflection. With a strong deflection. Why is it a strong deflection? Because the beta is um, relatively, the weight or the mass of the beta is very low. Yeah, it's almost zero. So it gets attracted quite easily to the positive plate. What about the gamma? Gamma is neither attracted to the positive or to the negative. It will pass through with no deflection. Okay. This is easy. This is easy. The harder part is the magnetic field. If I had the North Pole and a South Pole. If I had a North Pole and a South Pole. Again, alpha, beta, and gamma. Definitely the gamma also will not be deflected. خلاص, gamma will not deflect. خلاص, that's easy. Alpha and beta, how do they deflect? Using the Fleming left-hand rule. Using what? Fleming left-hand rule. Oh, Fleming left-hand rule. The alpha, we can't consider it to be the current in the Fleming left-hand rule. It's the current in the Fleming left-hand rule. Let me draw it in another way. Okay, easier. Okay, an easier way. I'll draw the magnetic field into the paper. I'll draw the magnetic field, into the paper. These X's mean that the magnetic field is directed into the paper. Magnetic field into the paper. Okay, I will use the Fleming left-hand rule. First finger is the magnetic field, which is into the paper. Second finger okay? The middle finger is the alpha. Fleming left hand rule, okay? It is the alpha. So if I direct the alpha, it's moving to the right, and the magnetic field is into the paper, so the alpha will move upwards. The alpha will move upwards with a weak deflection. It will move upwards. What about the beta? Definitely, the beta will move downwards. Again, the beta will move downwards. Why? Because it's opposite to the alpha. Can I find the beta? Yes, I can find the beta using the Fleming right-hand rule. Fleming right-hand rule. Again, the Fleming right-hand rule. The first finger is the magnetic field. Second finger, which is the middle finger. This is the beta. It's moving to the right, so the beta will be directed to the downwards. The force on the beta will be downwards, and the beta will move downwards with a strong deflection compared to the alpha.
Won't the beta move to the North Pole?
North Pole? No. No, no. It's never to the North Pole or to the South Pole. It's always at 90 degrees to the North Pole or to the South Pole. Okay? It's always at 90 degrees. It's always perpendicular to the magnetic field.
So I don't understand how we use Fleming's left-hand rule and we get two different answers.
No, two different answers because you have two different inputs.
Yeah, so what do I change when I do it?
What you change is your hand. You change your hand. Fleming left hand rule, and the other one I use the Fleming right hand rule.
Wait, so which one? Oh, which one did I use?
I just said it. I just said the Fleming left hand rule is the alpha, but the beta is the right hand rule.
Okay.
Okay? حلو. Um,
Sir, I'm still confused. This is just the same thing as the first diagram, right? Yani,
what first diagram?
the diagram you just drew.
On the
is
left?
Yeah, it's like the same thing as the one on the right, صح?
No, it's not the same thing at all. Why? On the left hand side, okay, I have an electric field. You have an electric field, which is different from a magnetic field. An electric field would very simply, very easily attract the alpha. The alpha would be attracted to the negative plate, and the beta will be attracted to the positive plate. That's easy because it's an electric field. But if you have a magnetic field, if you have a magnetic field, the alpha wouldn't simply, for example, be attracted to the South Pole or the beta to the North Pole. No, that's wrong. They wouldn't even be attracted to the poles. They move at 90 degrees to the poles, okay? They will move perpendicularly to the poles. The alpha, how does it move inside a magnetic field? You never know. You need to use the Fleming left-hand rule to detect the motion of this alpha inside the magnetic field. You have to use it. You have to use the Fleming left-hand rule to find the direction of the alpha inside this field. Okay?
بس
Uh,
بس we use a left hand for the alpha
and
and the
right
right
hand
hand
for the beta.
how would they make this question? I'm confused. I don't remember seeing a question like this.
They will give you a question like this, without these arrows,
Mhm.
and they will tell you, draw the deflection of the alpha, beta, and gamma inside the magnetic field.
And we don't have to explain ولا
No,
we'll do it.
you don't have to explain.
Wait, so هو على حسب in which direction the current is moving is على حسب ال deflection حق الألفا. So مثلا like if we were moving the opposite way, the alpha would deflect downwards and the gamma would deflect like قصدي the beta would deflect up ولا what?
If it was moving you mean from the right hand or from the right side to the left side?
Yeah.
Yeah, definitely
Okay.
it will move in
And
the
then
opposite way. Yes.
if it was left to right, it would just be زي ما احنا قلنا.
Yes. From left to right, the alpha will move upwards due to the Fleming left-hand rule, but with a weak deflection this way. Okay.
Mhm.
The gamma will move downwards, right-hand rule, strong deflection, the beta, and the gamma will not deflect.
Okay.
We can't see the North and South Pole here.
No, you cannot see it. That's why I stated that the magnetic field is into the paper. So your first finger, which is the index finger, is into the paper. Okay? Okay, yeah. Explain the relative ionizing effects with reference to the kinetic energy and the electric charge. Okay, the kinetic energy of the alpha is the least, and that's why it has the.
Wait, I'm sorry.
Huh?
When I do like the left-hand rule, I'm not getting it to go down.
Yes. لا, إيه?
Like this is into the paper, right?
Yes, this is
Like
into.
this,
Yeah.
like this is going this way. It's not going down.
No,
Or
this
up.
is the direction, initial direction of the alpha. But again, the thumb will indicate the force applied on the alpha. So
Oh, so when you want to draw the arrow, we use the thumb.
yes, yes.
Oh, okay.
Does the question tell us in the paper in or out? Yes, it does tell us whether the magnetic field is in or out. Yes, it does tell us. Okay. Continuing the radioactivity, although we don't want to get fixated on a um, very trivial point. Okay, it's only worth 1 mark in the exam. Well, know that the radioactive decay is a charge in unstable nucleus. Okay. Um, State that during an alpha decay or beta decay, that it changes. Yes, we know how it changes. Okay, I'll tell you now. We will calculate it. Know that the isotopes of an element may be radioactive due to the excess neutrons in the nucleus. Okay, why are they radioactive? Because they have a lot of neutrons. That's why isotopes are. That's why isotopes are um, radioactive. Why? That's why isotopes are unstable because they have too much neutrons. Okay. Describe the effect of alpha, beta, and gamma emissions on the nucleus. Okay. Instability, the reduction of number of excess neutrons. The following change in the nucleus occurs during the beta emission. We know that the beta emission. Okay. What happens in the beta emission? The neutron splits into a proton and an electron. That's why when a beta is produced, the number of protons increases by 1, the number of neutrons decreases by 1, but the total mass number remains the same. Okay, the total mass number remains the same. Okay, what happens in the beta or alpha equations? Very simply, we know that if an alpha is produced, if this is, for example, X, okay, let's say A and Z, it produces an alpha plus, let's say Y, but the A is -4 and the Z is -2, okay? If it produces a beta, 0 and -1, okay, again, X, A, and Z, what happens? It produces a Y. The Y would have I'm sorry, I wrote 0 and -1 wrong. Okay. Okay. 0 definitely is, and -1. So definitely the Y will have the same mass number, but the proton number will increase by 1, Z plus 1. The atomic number will definitely increase by 1. Okay. يلا. Half-life.
I
يلا
have a
قولي.
question.
Yeah.
When it says, this, wait, can you scroll up 1 second? Like in this part.
Hmm.
The changes in the nucleus. What do I say for gamma?
Gamma doesn't change the nucleus. Okay. Gamma does not change the
Yeah, so
nucleus.
so it won't ask me what's the change in the nucleus.
No, no, no. Gamma
Okay,
does
and
not
then
change.
alpha particles, I say it gains 2 protons.
No. The final nucleus will lose 2 protons and 2 neutrons. The total mass of the final atom will be 4 less, and the total atomic number will be 2 less. Okay.
Wait, then what about beta?
Beta will have the same mass number, but the proton number will increase by 1.
So I don't say a neutron will become a proton or an electron.
لا, that's if he asks you what in specific details what happens inside the nucleus. If he does ask you, then you have to say that the neutron splits into a proton and an electron. This electron is the beta that escapes, for example.
And then for if it said that for alpha, what do I say? Would lose
Alpha.
2 protons?
Yes, 2 protons
Oh.
and 2 neutrons. Okay. Yep.
wait so
Hmm.
أنا هو في اللي هي number 3 لو احنا طلعت سنة اللي هي بتاعة ال isotopes of an element may be radioactive هو يعني here إنه هو بيقول إنه there like if something is radioactive it might be علشان عندهم like excess of neutrons أو كده يعني لو جه سألني why it's radioactive أكتب كده صح؟
Yeah. Why is an isotope unstable? Because it has too many neutrons, for example. Okay? Because it's too heavy. It wants to get rid of these neutrons. Okay. Yeah. Half-life. Okay. What is the half-life? Very simply, the half-life is the decay of the radioactive source. Eventually, with time, the radioactivity of any source decreases. Okay? We need to measure the time for the radioactivity or for the mass to decrease to half the previous amount. For the time taken for the radioactivity or for the mass to become half the previous amount. Okay, this is what I mean by a half-life. I can calculate the half-life from a decay curve with or without the background radiation. Okay, if I calculate it without the background radiation, what will I do? For example, if this was 8,000 counts per minute, okay, to find the half-life, what should I do? 8,000 divided by 2, it would be 4,000. Using the 4,000, draw a horizontal line and then a vertical line, and then I will take the time. Okay, this is the time taken, for example, 7 hours. Okay, so the half-life is 7 hours. This is very simple. The harder part is if you have some background radiation. If you have some background radiation, it would be the same curve على فكرة. It would be the same curve. Okay, but for example, the initial count rate was, let's say 560. And I told you that there's a background radiation of 40. Minus, divide, plus. Okay, you have to remember this. Minus, divide, plus. You have to first subtract the background radiation, 520. Then you need to divide the 520 by 2, which would be 260. And then you add the background.
500.
Hmm?
540 minus 40.
560 minus 40 is 520. Okay, then you add the background radiation again, which is 300. Using the 300 now, we can find the half-life. Okay, minus divide plus whatever time it would take. This would be the half-life. Don't forget minus divide plus. ماشي? Okay. Yeah. Explain how the type of radiation emitted and half-life of the isotope determine which isotope is used for the applications including. Okay. The household fire smoke or the smoke alarms, they use the alpha particles. Irradiating food to kill bacteria. Okay. To kill bacteria, we can use gamma rays. Okay. Sterilization, gamma rays. Okay. Measuring and controlling the thickness of materials with the choice of radiations linked to penetration and absorption. This could use gamma. Sorry, this could use beta. Okay. The thickness of some materials, this could use the beta. Why? Because beta could pass through very thin materials, but very thick materials, beta cannot pass through them. Okay. Diagnosis and treatment of cancer using gamma rays. Again, so these are some very popular uses of the different types of radiations that we know of. Okay. Continuing the radioactivity, yalla. State the effects of ionizing nuclear radiations on living things. They have definitely some dangers. They could cause cancer. They could kill living cells. They could cause mutation. Okay. How does the beta get stopped? Again, the beta gets stopped by a thick sheet of aluminum. Beta gets stopped by a thick sheet of aluminum. Describe how radioactive materials are moved, used, and stored in a safe way. How do we store them? Using using lead containers. We have to use lead containers. Why? Because if they give off gamma radiations, then we would be safe from these gamma radiations. We need to use lead containers. Explain safety precautions for ionizing radiation in terms of reducing exposure time. We have some safety precautions. Reduce the exposure time, increase the distance between you and the source, and using some shielding. Okay, we know these three safety precautions. Decrease the exposure time, increase the distance between you and the source. Okay, don't touch the source with your hands. Use a shielding. Okay, some sort of hazmat suit or some sort of lead shield. Okay, to protect against the different types of radiations. Okay, and that's it. Unit 5, Atomic Physics. Any questions regarding the atomic physics?
Sir, there was a question in the February-March past paper. It was حاجة atomic physics. It was like a 4-marker, and I still don't understand كيف أجاوبها. Wait, let me try and see if I can find the.
I can solve it with you. Okay, right after we're done. Inshallah, we still have time. We can solve it together. Okay, inshallah. Any other questions regarding whatever I have explained? Okay, good. طيب. حلو. Space physics. Space physics was divided into 2 sections. First section was talking about the Earth and the solar system. Okay. The second section was talking about the um, universe and the galaxies. Okay. Let's quickly move through the Earth and solar system. We need to move very quickly because it was quite easy. The Earth rotates around its own axis in 24 hours. This gives us the apparent motion of the sun. The sun doesn't actually move. Okay, we see the sun rising from the east and setting in the west. The sun doesn't actually move. What happens is that the earth rotates around its own axis, and this creates the apparent rising and setting of the sun. Right? Know that the earth rotates around the sun in 365 days. This creates the seasons. Okay. You know all of the seasons. Okay. Know that it takes approximately 1 month for the moon to orbit the Earth. 1 month is about 28 days. One lunar month is about 28 days. So the moon takes around 28 days to rotate around the Earth one time. That's one lunar month. Define the average orbital speed. V equals 2 pi r over t. V equals 2 pi r over t, in which r is the average radius and t is the orbital period. Okay, for example, the orbital period of the Earth around the Sun is 365 days. If he wants the period in hours, then we have to multiply 365 times 24 to find the number of hours in 1 year. Okay? Define the average orbital equation. Okay, radius is usually we use the radius in kilometers. Usually, if he wants anything else, then we can convert easily from kilometers to meters or from kilometers to whatever other unit he needs. The solar system, our solar system, consists of one sun, one star, which we call the sun. It consists of 8 planets, 8 planets, which are in order. You have to memorize them in order. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. My very excellent mother just served us noodles. You can memorize it this way. We have one star, which is the sun, the eight planets. We have some dwarf planets such as Pluto. We have some asteroids. We have some comets. We have moons orbiting the planets. You have to know that the moons orbit the planets. We have to know that the planets orbit in an elliptical orbit, not in a circular orbit. Okay, the planets, minor planets, comets, they all have what? Hmm? Elliptical orbits, not circular. Elliptical orbits, it's like an oval. Okay, it's like an oval. Okay, and the sun is not in the center of this ellipse. The sun is usually to the left or to the right. So this is the sun, for example, and this is the motion of the Earth around the sun. This is the motion of the Earth around the sun. From this motion, we can, okay, from this motion, we can uh, find the kinetic energy and the gravitational potential energy of the Earth or of this planet while it is rotating around the sun. Okay, what happens when the Earth or when the planet is very close? When the planet is very close, what happens to its speed? It increases. Kinetic energy increases. As it moves away, the kinetic energy decreases. But the potential energy or the gravitational potential energy or the gravitational pull starts to increase. And that's why it gets pulled back and moves in. As it moves in, the kinetic energy starts to increase. And then it's like a slingshot. You throw it away, and then it moves all the way to the end of this ellipse, to the end of this orbit, and then it gets pulled back. Okay, kinetic energy keeps on increasing and decreasing. We will discuss this again, I guess, further on, inshallah. We need to analyze and interpret some planetary data about the orbital distance, duration, density, surface temperature, uniform gravitational field strength at the planet's surface. Okay, very simply put, okay, you could have a table. He could give you a table, for example, including 2 or 3 planets. Okay, and then from this table you can identify the distance of this planet. Okay, you can identify the duration, the orbital duration. You can identify the density, the surface temperature, the gravitational field, and then you can start to compare between different planets. Okay, you can start to compare between these different planets. Um, Again, moving on to the planets, we have 4 inner planets and 4 outer planets. The 4 inner planets are always, okay, the 4 inner planets are what? Rocky and small. Usually they have a higher temperature. The 4 outer planets are gaseous and large, and usually they have a lower temperature. Okay. We can use the accretion model for the solar system to know how these planets were formed. How were the planets formed? Again, very simply put, we had some nebula, some stellar nebula, which was a formation of some gas and dust and clouds. This gas and dust and clouds started to attract each other. Okay, the gas and all of the atoms inside it started to attract towards each other due to what? Due to the gravity. When they started to attract due to the gravity, what happened? The pressure and temperature start to increase. So initially, the first thing that formed in the solar system was the sun. Why? Because the temperature increased rapidly, okay? Its mass kept on increasing until the sun started to form. And later on, we will talk about the um, life cycle of the stars later on. But again, دلوقتي we will just assume that we had the sun formed because of the formation of or because of the attraction between the attractive forces between the atoms and the very small particles. And then there was still some planetary dust, some nebula rotating around this sun, okay, around this star that had formed. These nebula or this planetary dust or planetary nebula, what happened? Again, the rocks started, or يعني, the atoms started to join, forming small particles. These small particles started to join again, forming larger particles, even larger rocks, larger planets. Okay, and from there we started to form protoplanets. We started to form protoplanets, which all of the planets. Okay, the accretion model states that all of the planets are traveling in the same direction around the sun. They all travel in the same direction, clockwise or anti-clockwise. You're not required to know. Okay, but they are all traveling in the same direction and in the same plane. What do I mean they're traveling in the same plane? Yani, I don't have one traveling perpendicular to the other planet. No, they are all traveling in the same plane around the sun. Okay. The accretion model, we had a short video. I can show you the short video later on. Okay, I can just send you the link for the short video explaining briefly what is the accretion model. It's very easy to understand it. Okay, it's quite theoretical, but it's really, really easy to understand what the accretion model or how the solar system was formed. Okay, and due to this theory, all of the planets are rotating in the same direction. And due to this theory, again, the four inner planets are rocky and small and have high temperatures. The four outer planets are gaseous and large and have lower temperatures. These lower temperatures allowed these planets to get that large. These lower temperatures allow these planets to attract all of the gases that left the inner planets. The inner planets had initially had some gases, but due to the very high temperatures, these gases couldn't remain on these planets due to the very, very high temperatures because of their proximity to the sun. Okay. Okay. Yeah, moving on. Containing the solar system, know that the strength of the gravitational field at the surface of the planet depends on the mass of the planet. This is a really important point. And around the planet decreases as the distance from the planet increases. This is another important point. The gravitational field strength on Earth is what is 9.8 meters per second squared. What if I go to a planet which is much more massive than Earth, such as Jupiter, for example? Jupiter is much, much more massive than Earth. So definitely the gravitational field strength on Jupiter will be much greater than 9.8. It could be 15, it could be 20, whatever. Why? Because the mass of Jupiter is much greater than the mass of Earth. If I go, for example, to the moon, we know that its mass is much less than the Earth. So the gravitational field strength of the moon is much less than the gravitational field strength of the Earth. That's it. Okay? What about the second point? Around the planet, the gravitational field strength decreases as the distance between you and the planet increases. Now, we are all living on Earth. I guess that you are all living with me on Earth. None of you are in space now, right? Anyway, if we're all living on the Earth now, we're all experiencing the same gravitational field strength, which is 9.8 meters per second squared. What about the astronauts in space? Do they experience the same gravitational field strength of 9.8 meters per second squared? No, definitely not. Why? Because the distance between those astronauts and Earth and the surface of the Earth is much larger than the distance between us and the surface, because literally we're on the surface. If I took, for example, a plane, okay, and I traveled 40 or 50,000 feet above the surface of the Earth, will I experience a less gravitational field strength? Yes, I will. Okay. If I take, for example, a spaceship and I travel 120,000 feet above the Earth's surface, will I experience an even less gravitational field strength? Yes. So whenever I increase my distance above the surface, okay, whenever I increase my distance above the surface, the gravitational field strength does decrease. And that's it. Okay? That is it. ماشي. Calculate the time it takes light to travel a significant distance. Time it takes, we know speed equals distance over time. Speed equals distance over time. So time equals distance over speed. And we know that the speed is 3 times 10 to the power of 8 meters per second. Know that the sun contains most of the mass of the solar system. Yes, the sun contains 99% of the mass of the whole solar system. The sun is a million times larger than the Earth. A million times larger than the Earth. That's why it contains 99% of the mass of the whole solar system. Note that the force that keeps an object in orbit around the sun is the gravitational attraction. Definitely. The gravitational attraction of the sun keeps the Earth and all of the planets, all of the moons, all of the asteroids, all of the comets in orbit around the sun. Know that the sun's gravitational field decreases and that the other orbital speeds of the planets decrease as the distance from the sun increases, which is quite intuitive. Yes, the Earth is, let's say, quite close to the sun, but Mercury is even closer to the sun. صح? Mercury, Venus, Earth. Yeah, Mercury is the first planet. So it's the closest planet to the sun. That means that the gravitation field on بصوا, the gravitational field on Mercury due to the sun is much stronger than the gravitational field on Earth due to the sun, which is also, the gravitational field on Earth due to the sun is greater than the gravitational field on, let's say, Neptune due to the sun. Why? Because Neptune is very far away. The Neptune is pulled towards the sun. Yes, it is pulled towards the sun, but with a slightly, and not slightly, much less force. Why? Because its distance is much further away from the sun. Okay. Okay. Know that an object is an elliptical orbit. Yes, we just said that. Elliptical orbits, they travel faster when they are closer to the sun. Okay, and this is due to the conservation of energy. Yes, we just said that. Okay. Oh, when they are closer to the sun, this is the sun. When they're closer to the sun, the kinetic energy increases. As they move away, the kinetic energy decreases, but the gravitational pull increases. And then they get pulled back and keep on moving in this elliptical orbit. Okay. Any questions? Yeah. Yeah. Moving on to 6.2. Last lesson in our syllabus. The sun as a star, and then we will talk about the universe. The sun is a medium-sized star. Okay? We know that the sun is a medium-sized star. We must memorize that the sun consists mostly of hydrogen and helium. The sun consists what? Mostly of hydrogen and helium. And that's why the hydrogen keep on fusing to produce helium. They keep on fusing to produce helium. Most of the energy radiated by the sun. We have 3 types of energies radiated by the sun: infrared, visible light, and ultraviolet. You have to memorize them: infrared, visible light, and ultraviolet. Know that the stars are powered by nuclear reactions, and these nuclear reactions are called the nuclear fusion. Okay? Nuclear fusion, not just any reaction, not just any nuclear energy, no, nuclear fusion inside the stars. They fuse hydrogen into helium. خلاص, we have to know that. Hydrogen is fused into helium.
So how does the sun, like, how does it radiate ultraviolet?
How does it radiate ultraviolet?
Yeah.
Well, actually, the sun produces a large spectrum. It could radiate even more than ultraviolet. It could radiate X-rays. It could radiate less than the infrared. It could radiate, for example, the microwaves. Okay, the sun has a lot of nuclear reaction going on. This nuclear reaction could produce a large spectrum of the electromagnetic radiation. Okay, the waves produced could have large frequencies or low frequencies. Depending on the frequencies being produced by the nuclear reactions, okay, This could produce, or this could give a radiation of an ultraviolet radiation, or it could give an infrared radiation. Most of it is either light, infrared, or ultraviolet radiation. Okay, some of them could be X-rays, some of them could be microwaves, some of them could be gamma rays, radio waves. Okay, but the majority is infrared, visible light, and ultraviolet. Okay, yeah. We have to know that these stars. Okay, now let's talk about the galaxies first. The galaxies are made up of what? Of billions of stars. Our Milky Way consists of billions of stars. The sun is only one of these hundreds of billions of stars inside this Milky Way. Okay, and the other stars are much, much, much further away from us. The closest star to us, other than the sun, is about 4 light years away. What is a light year? Okay, what is a light year? It's a distance. Light year is a distance in which the light travels in 1 year. It's the distance in which the light travels in 1 year. طبعا in vacuum. If you have a laser beam, for example, and you turn on this laser beam for 1 year, okay, you will measure the distance it traveled. You measure the distance it traveled after 1 year, and you'll find that it is light year. Light year is approximately equal to 9.5 times 10 to the power of 15 meters. 9.5 times 10 to the power of 15 meters, which is almost 9.5 trillion, okay, kilometers. 9.5 trillion kilometers. That's a huge number. 9.5 million kilometers. Okay. 9.5 million kilometers. Describe the life cycle of a star. We can calculate the light year. How can we calculate the light year? It's the distance. Distance equals speed times time. What's the speed of light? 3 times 10 to the power of 8 times the time in 1 year. 365 days times 24 hours times 60 minutes times 60 seconds. If you calculate this on your calculator, it would give you 9.5 times 10 to the power of 15 meters. Okay? Distance equals speed times time. The life cycle of a star. يلا. Life cycle of the star. A star is formed from the interstellar clouds of gas and dust that contain hydrogen. Okay? Interstellar clouds. خلي بالكوا احنا we kind of need to read this 2, 3, 4 times, okay, to kind of memorize it if you don't already know it. If you already know it, that's great. If you don't already know it, then please try to read it more than once to kind of memorize it. The star, okay, how does a star initially form? Because of an interstellar cloud. These interstellar clouds contain mostly hydrogen. A protostar, what's a protostar? It's an initial star, okay? It's still a baby star. Protostar is a baby star, okay? How does it form? By the cloud collapsing and increasing the temperature as a result of its gravitational attraction. So the gravity pulls in all of these hydrogen atoms together. The gravity pulls in all of these hydrogen atoms together, and the temperature starts to increase. The temperatures increase to millions of degrees Celsius. Millions of degrees Celsius. When we reach these millions of degrees Celsius, the hydrogen atoms start to fuse. The hydrogen atom starts to fuse to helium atoms. How we know that part? A protostar starts to become a stable star. When does a protostar become a stable star? A stable star is in equilibrium. Stable star has to be in equilibrium. Our sun is in equilibrium. Our sun is a stable star right now. It is in equilibrium. How does the sun or how does the star become a stable star when it's in equilibrium? Due to two forces acting on the star. We have two main forces acting on the star, an inward force and an outward force. The inner force or the inward force is due to the gravity. It's due to the gravitational pull of all of the mass of the star. Again, the gravitational pull is inwards. So it pulls all of the atoms inside. This is the inward force due to the gravity. What's the outward force? The outward force is the force due to the nuclear fusion. الايه nuclear fusion. Nuclear fusion is explosions. Okay, it keeps on exploding, it keeps on giving off huge amounts of energy. These huge amounts of energy are always directed outwards. Again, we have inward forces due to the gravity, and we have outward forces due to the nuclear fusion. So a stable star is when these forces are equal. And the sun is now a stable star, and these forces are equal. Inward force due to gravity, and outward force due to high temperature or high pressure of the center of the star, which is due to the fusion of the hydrogen atoms. All stars eventually run out of these hydrogen atoms. Okay. Is the outward force heat? It could be due to the heat, yes. It could be due to the heat, it could be due to the fusion of the hydrogen atoms. Yes, it is an outward force. Eventually, after billions of years, okay, literally after billions of years, these hydrogen atoms will run out. We have only a limited, it's a finite number of hydrogen atoms. When the sun starts to run out of hydrogen atoms, what does it do? The outer forces, okay, listen carefully. Listen carefully. When the sun starts to run out of hydrogen atoms to fuse, then the outer force, listen up, huh? The outward force due to the fusion starts to decrease. صح؟ ما دلوقتي we have the sun. There's an outward force due to fusion. And there's an inward force due to gravity. Now, this outward force will start to decrease. Why? Because the hydrogen atoms are now running out. What will happen? The gravity is now much stronger than the fusion. So when the gravity is now stronger than the fusion, it pushes the core inwards. It creates an extra inward force. This extra inward force actually causes the helium atoms to start to fuse. Now, the helium atoms will start to fuse. When the helium atoms start to fuse, what happens? An even larger fusion force acts outwards. So now what happens is the fusion force is now greater than the gravity force, and the sun or the star starts to expand. Okay? It starts to expand. Again, why? Because it ran out of hydrogen atoms. When it starts to run out of hydrogen atoms, it actually fuses the helium atoms, which gives even more, okay, huge, greater amounts of fusion forces or fusion. Um, Anyway, the fusion is now greater than the gravity, and therefore the sun or the star starts to expand. When the star starts to expand, we have to differentiate between two types of stars. If you have a small or medium-sized star like our sun, okay, initially does the gravity decrease because the mass decreases because there are less hydrogen atom? Initially the gravity, no, actually initially the gravity increases. Initially the gravity increases. Why does the gravity initially increase? Because the fusion was less, because now it's not stable. Okay, the fusion is less because the hydrogen atoms were less. Okay, but eventually the fusion will become more because the fusion of the helium atoms is greater than the gravity, and therefore it starts to expand. Okay, now when it starts to expand, we have to differentiate between two types of stars: a small star or a medium star, a small and medium star, or a supermassive star. Small and medium stars, like our sun, will expand and become red giants. Okay, they will expand and become red giants. These red giants will eventually blow up and form a planetary nebula with a white dwarf in the center. our sun eventually will become a red giant. Our sun will become a red giant, which will blow up, giving off a planetary nebula with a white dwarf inside or at the center of this planetary nebula. But what if we had a much more massive star, 10 times 20, 50, 1,000, 1,000,000 times greater than our sun? What will happen? It will become a red supergiant, which explodes, giving off a supernova. Okay, a supernova containing hydrogen and new heavier elements, leaving behind a neutron star or a black hole, leaving off a neutron star or a black hole. Okay, and then this supernova may form new stars with orbiting planets. Okay, we don't care about this part. I just care about that if it is a red giant or a super red giant or a red supergiant. Red giant would be because of this, the mass of the sun or the mass of the star is quite small. This is relatively small. If the mass is relatively large, massive star, what will happen? It will become a red supergiant. Okay, that explodes into a supernova, creating either a neutron star or a black hole. Okay, this is the life cycle of a star. This is the life
Wait,
cycle.
Mister.
Hmm.
Wait, so our sun right
Yeah.
now, is it considered a stable star or is it considered
Yes.
a red
Right
giant?
now, it's a stable star. Okay. Our sun is now in the stable phase. After a couple of billion years, the hydrogen will run out and it will become a red giant. It will become a red giant, not a red supergiant. Our sun will become a red giant after a couple of billion years. And then when it becomes a red giant, it will explode, giving off a planetary nebula, and a white dwarf will remain in the center of this nebula. Okay. Yes, I will do that. Okay.
How do
Now,
we?
hmm.
I mean, is there a point where it becomes a black dwarf?
Yes, the white dwarf, if you leave it long enough, it will become a black dwarf.
Because it loses energy?
It loses
Or
the
does
energy. Yes, because it loses the energy. Yes. Okay.
I have a question في الحتة إنه when it expands it's because and it loses hydrogen and يعني inside the story صح؟
It expands. Why? Why does it expand? Because it runs out of hydrogen.
Yeah.
So it starts to fuse helium. When it fuses helium, the energy given off by the helium is much more, okay, it's much more greater than the energy given off by the hydrogen, and therefore it starts to expand rapidly. Okay, it's
Okay.
now the fusion is greater than the gravity.
Okay. Thank you.
Okay, you're welcome. Okay, so this was the um life cycle of a star. Now, the universe. We know that the Milky Way is one of billions and billions and billions of other galaxies. Our Milky Way it's approximately 100,000 light years across. The diameter of our Milky Way is only around 100,000 light years across. Okay, which is relatively a small number. Describe the redshift. Describe the redshift as an increase in the observed. We have a question. Is fusion of helium greater because it has a bigger mass? Yeah, you can say so. Okay. Describe the redshift as an increase in the observed wavelength of an electromagnetic radiation emitted from the receding stars. Yes. Now, when the scientists observed the very distant galaxies, they found that the light being produced from these very distant galaxies was red shifted. What do they mean by red shifted? It means that the wavelength, okay, increased. The wavelength increased and the frequency decreased. Meaning, okay, if you have a less frequency, if you have a larger wavelength, it means that it's moving away. It means that it's moving away. That's what we mean by a red shift. Red shift, okay, is what they discovered when they looked at the very distant galaxies. They found that the wavelength of the light being produced from these galaxies is slightly longer than the wavelength of the light produced on Earth. They concluded that these galaxies are moving away from us, meaning that the uh, meaning that the universe is expanding. Okay, meaning that the universe is expanding, and this was evidence to the Big Bang theory. Okay, Big Bang theory states that, well, now the universe is expanding. What if we go back in time? The universe will shrink a little. If we go even further back in time, the universe will keep on shrinking, shrinking, shrinking until it reaches an infinitesimally small point in the middle of nowhere. And this was the point at which the Big Bang started. It was a point, okay, very, very, very small point, full of energy, pure energy, pure energy. When it blew up, it started to form all of the atoms and all of the galaxies and all of the stars and planets. Everything we know of, it came from this very small point in the middle of nowhere. Also, there is some other evidence. Okay, we need to kind of study this. There is some other evidence for the Big Bang. One of the other points was something called the cosmic microwave background radiation, CMBR, cosmic microwave background radiation. Scientists, when they um, searched the universe, okay, wherever they pointed their satellites, wherever, okay, in any point in this known universe, they found some radiation. They named this radiation the cosmic microwave background radiation. It's some radiation they counted out. They found it to be equal in any direction. Whenever they looked, whenever they pointed their satellites, okay, in literally any direction in the universe, they found the same amount of cosmic microwave background radiation. This indicates that the whole universe was initially in one point. Okay. The whole universe was, if you go back in time, around 14 billion years ago, okay, the universe started from one single point of energy, one single point of pure energy. Okay, I'll explain that the CMBR was produced shortly after the universe was formed, and this radiation has been expanded, okay, into the microwave region of the electromagnetic spectrum as the universe expanded. Okay, it's found in every part of this universe. Okay, yeah. Know that the speed at which a galaxy is moving away from the Earth can be found from the change in the wavelength. And we kind of need to memorize this. The speed at which, okay, the speed at which the galaxy is moving away can be found using using the change in wavelength of the galaxy's starlight due to redshift. Okay. Know that the distance can be determined using the brightness of a supernova. Again, these are two very important points. Two very important points. The speed can be found using the change in wavelength. The distance can be found using what? Using the brightness of a supernova in that galaxy. And then we can use both these values to determine the Hubble constant. Okay, what's the Hubble constant? It's the ratio of the speed at which the galaxy is moving away from the Earth to its distance from the Earth. H naught equals V over D. H naught equals V over D. And to be honest, we kind of need to memorize the number 2.2 times 10 to the negative 18 per second. 2.2 times 10 to the negative 18 per second. We can use this number to determine the age of the universe. We can use this number to determine the age of the universe. How? 1 over h, no, it should be 1 over 2.2 times 10 to the negative 18. Okay, this would definitely give me a huge number. It would give me a huge number. This number is in seconds. Whatever number you find, okay, it would be a huge number in seconds. We can keep on dividing this number until we find the age of universe in years. It will be approximately 13.5 or 13.4 billion years. Okay. So if you divide 1 over h naught, 1 over 2.2 times 10 to the negative 18, it will give you a huge number in seconds. You need to change this number to years to find the approximate age of the universe in years. Or you can just find it in seconds if you want. It's up to you. Okay? And that's it.
Wait, so Mr.
Hmm.
The redshift
Yeah.
proves that like the planets are moving away from us.
That the
So it's
distant
supporting.
galaxies are moving away from us. Yes.
Yeah. So the redshift and the CMBR both support the Big Bang Theory.
Yes.
Okay. And like when he asks about the Hubble constant to find the age of the universe, we don't have to convert to year, right? We can put it as seconds.
Yeah, it depends on the question. If the question tells you to leave it as seconds, okay. If it asks you to convert the time into years, then you'll have to convert it to years. Okay.
Okay.
حلو. Okay.
Wait, do we also have to know the blue shift?
لا لا no
For
no no no. Only the redshift. What did we multiply to convert it to years? To convert the seconds to years, we just need to divide by 60, okay, then divide by 60 again, and then divide by 24, and divide by 365. Okay?
Or you can just do 1 over the Hubble's constant, so.
ما هو
To
1
get
over
the-
Hubble's constant will give you the time in seconds. It will give you the time in seconds. If you calculate it, you have the calculator. Can you calculate the number now?
Yeah, I did 4.5 times 10 power of 17.
4.5 times 10 to the power of 17
That's
seconds
the age of the universe in seconds.
in seconds. Can you divide it by 60, then by 60 again, and then by 24, and then by 365? Okay. Hmm. Hmm. The number should be around. Hmm. I can't hear you.
Oh, I got 1.4 times 10 power of 10.
1.4 times 10 to the power of 10. Yes,
Yeah.
this is correct, which is 14 times 10 to the power of 9. 14 times 10 to the power of 9 means billion. Times 10 to the power of 9 means a billion. So 14 billion years, which is correct. Okay.
Sure, so when they ask us, yani, for the age of the universe, we just do 1 over h naught and then that's it.
Yes, that's it.
But isn't it a 4 marker?
No. CJ, it could be a 2 marker, it could be a 3 marker. Okay, if it's a 2 marker, it would be in seconds. If it's a 3 marker, it would be in years.
And then بالنسبة للredshift they would just ask us يعني the definition of it ولا what else?
Yes, what's the redshift?
They're
Okay,
probably gonna say, how do you find the speed of a galaxy moving?
And we just say using the redshift.
yeah. Okay.
بس هما if they say مثلا they're like explain the redshift
Hmm.
احنا
What is the redshift?
Change
It
in
is
wavelength.
the
it
wavelength,
is
or that when scientists looked at the very distant galaxies, they found that the wavelength of the light produced from these galaxies was longer than the wavelength of the light produced on Earth, indicating that these galaxies are moving away from the Earth.
okay, so we just compare the two wavelengths and then we just say blah blah away from Earth.
Yeah.
Okay.
Okay?
Mr.
Yeah.
So the idea of light years is basically like how many years it would take for us to find out if
No.
a star exploded.
What's a light year?
It's the distance that light travels in a year.
It's the distance that light travels in the air. Okay, so when you're talking about light years, you're talking about the distance. You're not talking about time. When you're talking about the
Okay.
light year, you're talking about the distance. For example, the closest star to us is called Proxima Centauri. I don't know how to actually say the name. Anyway, this star is 4 light years away from Earth. What do I mean when I say that this star is 4 light years away from Earth? I mean that the light, okay, travels, or the time light travels, time it takes for the light to travel from that star to Earth is 4 years. Again, I don't understand. What does this mean? It means, for example, if um, if that star explodes today, this second, right this second, if it explodes right this second, will I ever know? No, I will not know right now. I'll know in 4 years. After 4 years, I will find that this star has exploded. Okay? After 4 years, not today. Even if it explodes today, yes, even if it explodes today, you will never know. Okay? You will only know in 4 years. Why? Because the light will take 4 years to travel. The light of this explosion will take 4 years to travel from that star all the way to Earth. And that's what 4 light years means. Okay. When I say, for example, that the width of the Milky Way is 100,000 light years, it means that if you have a laser beam and you start a laser beam from one end of the Milky Way, this laser beam will take 100,000 years to travel from one end all the way to the other end. Okay?
Okay.
Okay. Okay.